All right, we got about another minute or so before we start the lecture today. And please remember to use the text channel of today's date for all the text communication. The YouTube link is already up, and as far as I can see, it is working. So for those of you who prefer to use the YouTube live stream, you can go ahead and go there. There is a significant lag compared to Discord, and that's why I prefer to use the Discord screen share function. But you can definitely use the other one if you want to. So what we'll do today is to go over the homework assignment, which is going to be due in 30 seconds. And then we're gonna move forward and talk about the ungraded assignment that I gave you guys the other day. Basically we want to look at the examples why one of the two conditions in the conjunction is not sufficient to define Cartesian product. So we'll go ahead and take a look at that. And we got 5 more seconds. And it is time to get started. Alright. So I hope everybody got enough time to work on the assignment for set theory, which is this one here. So we'll go ahead and go over the questions just kind of quickly and see if there are any questions. Alright, so I am aware that somebody is typing in the text channel, but until the question is up, I will continue to talk about the questions. So question number 1 is giving you the definition of A and B, and is asking which of the following is true. So in this case, A is a subset of B is true, but we also want to make sure the other ones are not true. A is an element of B, that is not true. B is a subset of A is not true. B is an element of A is also not true. So only the first choice is correct. Alright, so we got a question. We won't be able to see which question we got wrong. No, I think you can see it now. If you refresh, you should be able to see it now, because it just won't disclose the correct answer until after the due date. So give it a try and see if that happens. And oh, okay, so that works. So meanwhile, we move on to question number 2. So question number 2 is one question that I have to grade, and because it's based on an actual entered text. And someone says Ivan says he cannot see the correct answers just yet. So I don't know for sure, because when I pretend to be a student, it doesn't. Okay, so it doesn't work yet. Okay, maybe it depends on question number 2, because unless I grade number 2, it may not show the correct answer. But that's also why I'm going through all the questions now, so that you can actually see which one you got right. So just kind of, follow along, so this way at least you know which answer is correct. So for question number 2, it is a constraint type of question, which is kind of what I like to use also in exams. So this one gives you some definitions. It says the union between A and B contains the elements A, B, C, D, E, and then the difference between A and B, things that are in A but not in B, consists of C and E. And we want to define membership arrangement, which means I want you to tell me what is in A and what is in B. So there are actually quite a few options for this one. What we know for sure is when you look at all the elements between A and B, they must be A, B, C, D, E. We also know that C and E are things that are in A but not in B. So we can use that as a starting point. So we can basically say we know for sure that A has C and E in it, and B cannot have C or E, because otherwise, C and E would not show up in the difference. So now we can say, okay, but how do we get the union of A and B to have A, B, C, D, E? Well, if set B has A, B, C, No, A, B, D, sorry. So if B has A, B, D as elements and then A has C, E, that will meet both of these constraints. Okay, it will meet the requirements. But it doesn't mean that this is the only answer, because A can also contain the elements of A, B, or D. Okay, so A can have additional elements. Because if set A has element A, it's okay. It's not a problem, because A minus B are elements that are in A but not in B. So it's okay for A to have element A, element B, or element D. So those are all okay, correct answers. So do we have any questions about number 2? This is one of many, but you can also kind of imagine that A only needs to you just need to make sure that A has C and E, but it can contain the other 3 elements if it needs to. All right, so we got one question coming, or someone is typing. May not be a question, but all right. So we got 2 people typing. I'm gonna wait a little bit. All right, so here are the questions. It can be or. Okay, so there are 8 possible answers for A. There are 8 possible answers, because the presence of the elements A, B, D are optional. Okay, so A must have C, E, but other than that, there are, you can optionally also have A, B, D in it individually. So A can be absent or present, B can be absent or present, and then D can also be absent or present. So all of those are considered correct answers. B, on the other hand, doesn't have a whole lot of choices. B must have A, B, D in it. All right. All right, so let's wait until I get to question number 6, because I'm going through the questions one by one. Okay, so we're moving on to question number 3. Choose the correct answer. I'm just asking you to evaluate whether A is an element in a set where the only element is the set of with A in it, and the answer is false. It is not true. Okay, so I'm just kind of checking the text channel. No questions about this one. Very good. Moving on to question number 4. ABC is a set. ABC is also a set. So the question is asking, is a set a subset of itself? And the answer is true. It can be a subset of itself. Okay, it is not a proper subset of itself, but it is a subset of itself. No questions about that one. Moving on to question number 5. So question number 5 is asking, is the union between the set that contains ABC and the set that contains AB, is that union the same as the set that has ABC in it? And the answer is true. There we go. Because you cannot have duplicate elements. Okay, so it's not like the union between ABC and AB would be A, B, B, C. That is not true. So now we get to question number 6, which is what Lee Yu wanted to talk about. Okay, so we'll take a closer look at this. Regardless of the definitions of A and B, in other words, you can make A and B whatever you want. Okay, is the following always true or not? Does this implication always hold? That is what the question is asking. So we take a look. Okay, so we can interpret this in many ways. Okay, but we can just kind of go for the intuitive understanding. If A and minus B is an empty set, that means there is nothing in A that is not in B. Okay, there's nothing in A that is not in B. Does that imply it is not the case that A is a subset of B? So the only time that this implication is not going to be true is when you can find me a case of A minus B is non-empty, sorry, I take it back, where A minus B is empty, but this is false. In other words, A is indeed a subset of B. Okay, so let me say that one more time. If you can find me a case where A minus B does equal to the empty set, and at the same time A is also a subset of B, then the answer will be false. Otherwise, the answer would be true. So that is what it's asking. So what do you think? Now, if A minus B is an empty set, there's nothing in A that is not in B. And A is a subset of B also means that everything in A is also in B. But there are other cases where A minus B is an empty set, but A is not a subset of B. Alright, so let's take a look at a few examples. Okay, so we'll go ahead and take a look at a few examples using the tablet. And I do have the stylus today. Sometimes I don't, I misplaced the stylus and I have no idea where to put it. But today I got it. Alright, so we'll say, let's say A equals to the set that has ABC in it. And let's say that B is the set that has 0, 1, 2 in it. Okay? So now we ask A minus B equals to the empty set. That is true. Okay? And now we evaluate the other side, which is it is not the case that A is a subset of B. So in this case, A is a subset of B is clearly false, right? So now we look at the entire thing, and it is true. So this particular example does not make the implication false, because true implies true. Okay, so let's take a look at a different scenario where A is AB and B is ABC. So in this case, A minus B is an empty set. It's true because there's nothing in A that is not in B. So this part is true. Now we look at the implication, and we look at A is a subset of B. So in this case, A is a subset of B is true. Okay, this is not just subset of, this is proper subset of. So in this case, A indeed is a proper subset of B, which means the entire negation is false. Okay, so there is a way for me to construct A and B such that the left-hand side of the implication is true, but the right-hand side of the implication is false. So that means the claim that regardless of the definitions of A and B, this is true, that claim is false. It is not universally true. Okay, so that means this implication can be false. All right. Yes, it is the proper subset operator, Andrew. So Andrew is correct about that. And then Li Yu just used a single word, not. So I'm not really sure what that is referring to. And we are going to move on to question number 7. And Aiden is typing, so I'm going to wait a little bit. If you have not watched, there's a Netflix, I guess, documentary called Social Dilemma. If you haven't watched it, you should watch it, because they basically talk about how the dot 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 here when you're messaging, the dot 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 is actually part of social engineering to get people to stay on their devices a little bit longer. All right. So Aiden is asking, so if it was A minus B is an empty set and B minus A is an empty set, implies not a subset of B, it would be true regardless of how we define A and B. All right. So once again, so I'm gonna type it on the tablet, which is already up. Okay, so we'll use a new page. Okay, so let's answer the question. So A minus B is an empty set. Okay, and B minus A is an empty set. And then this entire thing implies it is not the case that A is a subset of B. All right. So when we look at this particular implication, then we ask, well, can we make this true and then this false? Because if that cannot happen, that means the implication is always true. Okay. So the first thing is, how do we make A minus B is an empty set and B minus A being an empty set? So when you look at A minus B being an empty set, it is basically saying there's nothing in A that is not in B, and then the other part is saying there's nothing in B that is not in A. So the only way you can make this part true is A and B must be the same. Okay, so basically this whole thing being true implies that A equals to B. So now we look at A equals to B. So if A does equal to B, then A is a subset of B is true. And then you have a negation in front of that, which means this entire thing is false. So in this case, this claim is not true. Okay, it's not always true. It's not always true. If you change the subset to a subset, proper subset of, then the answer would be different, because a set cannot be its own proper subset. Oh, okay, so if you change the proper subset, then it does change quite a few things. So we want this to be a proper subset and not just subset of. So now we changed the subset to a proper subset. So A being, because we know that A equals to B, and in that case A is a proper subset of B, would have been false, then the negation of that would be true. So A being the same as B does not make the implication false. And that's the only chance to make the implication false. Because if A does not equal to B, then the conjunction is going to be false. If the conjunction is false, or if the left-hand side of an implication is false, then the implication is always true. But does that kind of answer the question? Okay. All right. So okay, excellent. So now we move on to question number 7. Okay. So the question number 7 says, A intersecting with B equals to A union with B. That equality implies A equals to B. So now the question, it's the same thing, okay? If you can find me a case where the left-hand side is true but the right-hand side is false, then we can say false. But for all other cases, if that is not possible, then we have to answer true. Oh, tablet is in the way. Got it. There we go. All right, so A intersecting with B equals to A union with B. So what does that mean, right? So if A intersecting with B, which means everything that is both in A and B, equals to A union with B, which means everything that is in at least one of them, that does imply A equals to B. Okay, so the answer of this one is true, because there is no way to make the left-hand side true but the right-hand side false. All right, so that is number 7. And we're moving to number 8. So with number 8, we have A as a set is an element of B. Does that imply it is not the case that A is a subset? Okay, not a proper subset, just a subset of B. The answer is false in this case, because I can make it so that the case I can make a case so that A is as a set is an element of B, and yet at the same time it is not the case that A is a subset of B. That is actually fairly easy to construct, so let me go ahead and construct it. So we want A to be an element of B, and we want A to be also a subset of B. Okay, that's actually pretty easy to do. So I can define A to be the set of. Okay, if you want this to be super tricky, well, I wouldn't say super tricky, but a little bit tricky, we'll say A is an empty set, because the empty set is always a subset of any other set, right? So if A is the empty set, then I can make B the set of the empty set. So in this case, A is an element of B, is true. A is a subset of B, is true. This part is true, which also means the negation of true is false. So now I have a case where the left-hand side of the implication is true, but the right-hand side of the implication is false, which means the implication itself is false. So that's why for question number 8, since I can, there is one way, at least one way, to make the implication false, then to claim that this implication is always true is false. Oh, can't see the tablet. Thank you. I keep forgetting to switch. There we go. Tablet not in the way. Good. Okay. Alright, so does that help? I just constructed the case, A being the empty set, B is the set that contains the empty set. So A as an empty set is an element of B because B does have the element of an empty set. And at the same time, A is an empty set. It is always a subset of any other set. So this part, A is a subset of B, is true. But since I have a negation in front of the subset of, so now the negation is false. Now we have true implies false, which means the implication itself is false. And that's the answer to that one. And if I click Submit Quiz, it should grade all of the ones that can be graded automatically, and then the ones that cannot be graded automatically would be left alone. So this one, it says not yet graded, because it requires a person to grade that one. And the question 3 is correct, 4 is correct, 5 is correct, 6 is correct, 7 is correct, and 8 is also correct. Oh, okay, there we go. So I just verified all of these answers are correct, except for the one that I need to grade manually, which is question number 2. Any other questions about the homework assignment? Tablet is not in the way. Alright, so there are no questions. Alright, so if there are no questions, we're going to move on to talk about the other, the ungraded assignment. For more practice, I'm not really sure that. I don't know yet. Okay, so I do not yet have another place for more practice on this topic. I can think about making a little bit more. But if you're asking, are there any more practice? That means one particular concept is not entirely clear. So we can try to clear up that concept if you can identify which one is the issue. And what we will do today is we are moving on to the Cartesian product thing. Why we have a conjunction, in order to define that, in order to define what it means to be a Cartesian product. Okay. Okay, so I will think about giving you guys more exercises in terms of understanding the concept of a set and the operations related to sets. All right. Yeah, well, that's why I don't want you guys to use YouTube. That's pretty. There's a reason why I told you guys to use Discord, not YouTube. So if people insist on using YouTube because they don't want to use Discord live stream, I cannot do much about that. Um, because Discord has a mobile app and it also has a desktop app. You just have to install the mobile or desktop app and just use Discord. All right. Yeah. Well, it is normal, but it's not a. It does make it difficult to participate in class in a synchronous fashion. So that's all I'm saying. All right. So getting back to Cartesian product. So with the Cartesian product, um, I claim that we need this conjunction to properly define what is a Cartesian product. So what that means is I can make the left-hand side true with a set that claims to be the Cartesian product, and yet it is not a Cartesian product. Okay, so I'll give you an example. So I need to turn the tablet back on, and I'll give you an example. So let's claim that A has 1, 2 in it, and we claim that B, oops, okay, let me erase that, and then we claim that B has A, B in it. Okay. Now I claim that A times B, or the Cartesian product between these two, has the usual suspects. Okay, A1, sorry, I said one thing and then I wrote another thing. 1A, 1B, 2A, 2B, and I add this 2, 2 in it. Okay. Then you guys go like, but Tack, that is totally wrong because the Cartesian product should not have 2, 2 in this case. Well, let's see whether it will make the conjunction true or not. Okay, so let me see how I can do this. I'll just replicate the left hand side of the conjunction, which is for all x in A, for all y in B. It says xy should be an element of a Cartesian product with B. Okay. So we are looking at a Cartesian product of B defined in this way, and we are looking at this particular statement, and we ask, is that true or not? Okay. So for every x in A, which is 1 or 2, for every y in B, which is A and B, we can clearly see that all of them are inside what I claim to be the Cartesian product of A and B. Then you guys go like, what about that 2, 2? Well, that 2, 2 is an extra thing, but it does not make this condition false. So that means this way of defining the Cartesian product is not sufficient because it is allowing extra things in the Cartesian product when they're not supposed to be there. All right. So now we turn around and we say, what about the other side? Isn't the other side already sufficient to define Cartesian product? Well, let's take a look. Okay, so the other side says, for all 2 tuples xy in a Cartesian product with B, the following has to be true. Okay, x is an element of A, and y is an element of B. Okay, and in this case, I can make I can erroneously define a Cartesian product with B, such that this claim really so that this condition is true, but it really does not define Cartesian product properly. Okay, so we'll go ahead and use the same example. Okay, A is defined to be 1, 2, and then B is defined to be A, B. Okay, and then this time I claim that, hey, this is the Cartesian product between A and B. It only consists of one single element, which is 1A. And you guys would go like, but Tack, what about the other stuff that is supposed to be in A times B? They're totally missing. Okay, this definition of a Cartesian product with B is wrong. Okay, but we want to see whether it will make the condition true or not, right? So now we go back and look at this condition here, okay? And we ask, well, what is one element of A Cartesian product with B as defined here? 1A, right? So now we ask, is 1 an element of A? Yes. And is A an element, the element A an element of B? And we go like, yep, that is the case. So we just made the condition, we made this condition true, but yet using the wrong definition of the Cartesian product between A and B. So what it really boils down to is this one is not sufficient because it allows extra things to be in a set and still be considered as the Cartesian product. And then this one is erroneous in the opposite way. Okay, it can allow us to be missing items to be in a Cartesian product, and yet the condition is true again. But when we combine these two, then we're basically saying you cannot have extra things. Okay, this one says no extra stuff. Okay, this one says cannot miss items. So when you combine these two, then we have the proper definition of your Cartesian product. So this is important, okay? Not only because this is a really obscure way to define what a Cartesian product is, but it is a way to think about things. Okay, can we come up with an example so that we make one side true, but and yet it does not sufficiently define, or it does not express what we want to express. Okay, so there's a lot of stuff in this class that involves, can you think of an example that blah blah blah, okay, satisfies a particular constraint, or the opposite, not satisfying a particular constraint. So there's a lot of constraint-based reasoning in this class, and if you get used to that type of thinking, it'll be very helpful. Constraint-based thinking is also very helpful when you need to find test cases for programs. So it's kind of cool in that way. Alright, so Jonathan is typing. I can't really parse the top formula. Can you go over that for me? So I'm guessing you're referring to this one over here. Is that correct? Okay. So it says for all x in A, and then it says for all y in B, xy as a two-tuple is an element of A Cartesian product with B. That's what it's saying. So that is how we parse it. Now, just knowing how we say it in English does not automatically imply that we understand what it means. How is 2 part of the top one? Okay, so it is not. It's not supposed to be, but 2 being in what I define A times B would not make this condition false, because this is only for checking for proper membership. So having extra members does not, how should I put it? If I define the Cartesian product using only this portion, then we can allow extra members in a set in what we think is the Cartesian product, and as a result, this is not the proper way to define. But it's not proper when it is by itself to define the Cartesian product. Okay. All right. So any other questions? Oh, okay. So we got Aiden typing too. And then section 8, I'm just waiting for Aiden to finish typing. Okay, because it says exactly, it does not exclude stuff that should not be in the Cartesian product. It only specifies what should be in it. So that is the problem of the first of the top one. And then the bottom one is the opposite. It basically says, what really should be in it, but it doesn't. Okay, I take it back. The second one being this one over here, it says, um, um, let me see how I should put it. It says, whatever is in the Cartesian product, what condition it must satisfy, but it doesn't, it's not complete. It just says, hey, if you pick me something from inside this set, it has to satisfy this condition. But it doesn't, it's not complete, which means it doesn't give me everything that should be in it. It just says, well, if you give me one of those items, I can tell you whether it really belongs there or not. Alright, so now we move on to section 8, which is how we define subset using the quantifiers. So A is a subset of B if and only if every E in A, for every E in A, E is also in B. Okay, that's kind of one way to say it. That kind of makes sense, right? If you look at every single thing in A, and if that thing is also in B, then we can say A is a subset of B. A is a proper subset of B if and only if the first one, okay, because I know how I want to repeat that entire thing, so I just reuse, A is a subset of B. And so we have one extra condition to make A a proper subset of B. There has to exist at least one thing in B such that that thing is not in A. So that's kind of, using quantifiers to revisit, how we define the concept of subset and proper subset. Oh, okay, I keep forgetting that. Okay, I need to give you guys one of you guys control over the tablet, or whether the tablet is overlaying on top of the other screen or not. Because I keep forgetting, because I can't see it when I'm typing like this. Okay. Are we good so far? Alright. Alright, so assuming we're good, then the next module, okay, if we go back to the class, I'm just going through the modules like one by one, sequentially. So the next module is functions as sets, okay? And this is the module, and this is the module as, its own page. So the first concept is tuples, and we talked about this already. A tuple is essentially an array. It's really just an array or list. Okay, things are ordered, and you can have duplicate items. Okay, and this is where you can say the first thing, the second thing, the third thing, and ordering is important. Okay. All right. So that's not section 2 is really just a mentioning of something that we have already talked about, and also the notation. So given the T is a tuple, we can use what we understand as the subscript or the indexing operator to refer to one of the items inside a tuple. So now we look into functions. So in functions, you have encountered this concept in many other math classes already. Because you have already met Math 370 or Math 372 as a prerequisite of this class, so you must have encountered functions already. So in math, it is not uncommon that we define a function like f of x is 2x, so that in for a particular instance, f of 2 is 4, and so on. But in this class, we look at functions in a slightly different way. We look at functions as a map, okay? And the way we define that, it takes us a few terms to get to that point. So we basically look at a function as a map that map elements in a domain, okay? This is where things are coming from, to a destination set, which we call a codomain. So the domain is what can go inside the parentheses as you apply the function, and then the codomain is where you can find the answer after you apply the function. In other math classes, the word range can also be used to mean exactly the same thing as what we call a codomain, basically the destination of the mapping. Okay. So when we describe a function, this is a notation that says, f is a function, whereas x is the domain and y is the codomain. That is all that it is identifying. Okay, so this notation is once again identifying three things. It is identifying that f is a function, x is the domain of f, y is the codomain of f. That is all it's saying. It doesn't really say anything about, but how are we mapping things from x to y? That it doesn't say that at all. Okay, all it says is x is the domain, y is the codomain. So now we want to go back to the example of f of x equals to 2x, and we want to see how we can apply the terminology that we have just introduced. So now you really kind of have a choice, okay, of what you want to use as the domain. You can use natural numbers as the domain. You can use counting numbers as the domain. You can also use integers for the domain. Okay. What about real numbers? Well, sure. Okay. In all of your other classes, typically the domain and the codomain are real numbers. But in this class, we do not use real numbers. And there's a reason. It has to do with how this class is named. Okay, this class is named discrete structure or discrete math, depending on where you hear about this name. But discrete means one particular thing that we haven't really encountered yet. Okay, real numbers are not discrete. Okay, they're not discrete, not in the sense of they are not decent, that sort of discrete. They're not discrete in the sense that between any two different real numbers, there's an infinite number of real numbers between that. If you know A is a real number, B is a real number, there's an infinite number of real numbers between A and B. But you cannot say the same about integers. Okay, if I give you two integers, there's a finite number of integers in between, possibly 0. Okay, because if I say here's 3 and here's 4, tell me all the integers between 3 and 4, excluding 3 and 4 themselves. Then you say that's going to be an empty set. There are no integers, okay, between 3 and 4, excluding 3 and 4 themselves, right? But even if you include 3 and 4, it is a set that has a finite number of elements. So whether you include or exclude the n's, within a range, doesn't really matter in this discussion, because it has to do with whether the number of elements between a particular member and another member in this particular set is infinite or not. Okay, so that is why we only want to work with natural numbers. Okay, and there's something special about natural numbers which we will talk about when we get to a future module called Aleph Null, but it is not, we're not there yet. Okay, but natural numbers hold a kind of special place in this class, but we'll get to that point at some point. So getting back to this particular example, so for what I want to define, I am going to say let's just use integers as our domain. Okay, and integers is all the set of all integers is usually represented as a funny looking z, with a double bar, and we'll also, at the time being, we'll also say the codomain, which is also known as the range in some other math classes. We'll also say that is the set of all integers. Okay, so in other words, if we want to use this notation over here, the domain is the set of all integers. The codomain is also the set of all integers. Okay, that's how we are defining f is a function mapping integers to integers. But what do we do about but how do we illustrate the actual mapping from integers to integers? Well, this is how this is where the two tuples come in handy. Inside each two tuple, inside a set that is representing the function, the first item is an element coming from the domain, and the second item is something that is coming from the codomain. The two tuple itself, each two tuple, is representing a single mapping of one element from the domain to the corresponding element in the codomain. So in this specific case, we are saying 0 is mapped to 0, 1 is mapped to 2, 2 is mapped to 4, 3 is mapped to 6, and blah blah blah. And with blah blah blah, okay, if you're taking an IQ test and the IQ test is asking what is the next thing in the sequence, then you go like, most likely it's going to be 4, 8, and then we have 5, 10, and so on. That would be correct. But it is still not a very good way to illustrate properties of this particular set. So we are using a set to represent a function in this case. So using the notation that we have already talked about before, this is a little bit more concise, and it also tells you a little bit more about the membership in F. Okay, what are the elements in F? So all this is saying is everything in F should look like a 2-tuple. And within a 2-tuple, we have a value x, and then we have twice the value x as the first and the second item inside the 2-tuple. But that doesn't restrict where x can come from, so we kind of have to say such that x is an element of the set of all integers. So this is a proper way to define a set that has an infinite number of elements, and that particular set is also serving as a function in this case. All right, so I'm not seeing any questions. All right, so we are moving on to this notation here. So this notation here is basically exactly the same thing as this notation. They're just two different ways of saying the same thing. So this one says, for all x in Z, for all y in Z, y equals to 2x if and only if xy is in F. But it really is saying exactly the same thing as this one, except it is a little bit longer. Alright, so I got some question. Ivan was typing in the text channel, so I'm not sure whether there is a question or not. Alright, maybe not then. Alright, so if there are no questions about that, we're going to move on. Oh, what comes after the IFF? You mean this part here? xy as a 2-tuple is an element of F. That's all it's saying. Okay. Alright, so section 3.1 is taking a closer look to what makes a function a function. So I'll give you examples of what is not a function. Okay, so I'm getting back to the tablet, and I'll give you some examples. So in these examples, X is going to be a finite set, or a set with a finite number of elements. So I'm going to use 1, 2 in this case, and y is also going to be finite, and I'll use a, b in this case. And then I would say, okay, let's take a look at a few examples. So we'll look at F as a set, and it goes from 1 goes to a, and that is it. Okay, this F is not a function. Okay, is not a function. F using x as a domain and y as a codomain. Okay. Now, if you change the domain and the codomain, I can make this indeed a function, but not with x as our domain and y as our codomain. Okay. Let's take a look at a second example. Okay. So we have 1a, and then 1b, and then 2b. Okay. This is also not a function, and in this case it is not a function regardless of how you define x and y. But in this case, if I use this x, which has 1 and 2 as members, and then if I use this y with a and b as members, this F cannot possibly be a function. Okay. So now the question is, So what is the extra requirement of what a function is? Okay, so that's what section 3.1 is going to talk about. So we'll go ahead and look at the notes again, and this time we take a look at the first requirement of f being a function. If x is the domain and y is the codomain, then a function f going from x to y has to be a subset of the Cartesian product between x and y. That kind of goes without saying, right? Because we want the two tuples in f, so that the first item comes from the domain and the second item coming from the codomain. So this subset of is kind of like, yeah, that's kind of obvious. So now we want to look at the other requirements. So the other requirement is each element of the domain must be mapped to one and only one element in the codomain. So I'm just highlighting the sentence that I want you guys to focus on. So this particular sentence can be ambiguous. Okay, to some people it can be ambiguous, but hopefully to most people in this class it is not ambiguous. In other words, there's only one way to interpret this statement. Each statement, each element, which basically means it doesn't matter which element of the domain you're looking at, it must satisfy this requirement. So we'll go and take a look at what requirement are we talking about. Must be mapped to one and only one element of the codomain. Okay, so if we say just one, then it is ambiguous. If we just say that it must be mapped to one element in the codomain, then we can say, can we have two? Can we have three? That one is kind of ambiguous. And if we say, map to only one element in the codomain, it is also kind of ambiguous, because we can say, can it map to nothing in the codomain? Kind of ambiguous. But when we say one and only one, it is not ambiguous anymore, because it excludes the possibility of more than one. It also excludes the possibility of none. So that is why we use the phrase one and only one sometimes, because it really helps to clarify how many we are talking about. So do we have any questions regarding the use of this phrase, one and only one? Okay, no questions. All right. So now we look at this entire requirement of what it means to be a function given a particular domain and given a particular codomain. We ask, but heck, are there any other ways to specify this in a concise and yet precise way? Okay, because that's what mathematics is about. Okay, mathematics is a lot of things, but first and foremost, mathematics is a language. It's just like English, it's just like Chinese, Vietnamese, Russian, Farsi, and so on and so forth. It is a language. It allows people to communicate concepts in a very precise and most of the time concise way. Unfortunately, natural languages are not concise nor precise in many cases. So now we want to ask, can we say this using a concise and yet precise way? Okay, that's what we are trying to shoot for in section 3. So now we'll go ahead and take a look at one particular obscure thing like this one here. Okay, so we're going to take a look at this not equation, but statement, and then we try to understand what the statement is really saying. So what we'll do is we are going to decipher this statement step by step. So just give me a little bit of time to copy this onto the tablet, and then we'll use the tablet to explain how we can look at this. Okay, so we have Alright, so I just got it entirely copied, and now we switch to the tablet. Alright, so there's a lot of stuff, right? So I'm not sure how many of you get the sense that this is overwhelming. I cannot do this. You can do this, okay? It may look complicated, but there's a structure to it. So the idea is, how do you unravel the structure so that you can understand which piece relates to which other piece in what way, okay? And most of the time, you can either work your way from outside in, or you can work your way from the inside out, okay? But in this case, let's go ahead and start with this part here. This is our quantifier. It basically says it doesn't matter which element you pick from the domain, which is represented by the set X, the following has to be true. Okay, so basically it's saying, for every element in the domain, this entire portion needs to be true. That's all it's saying, right? Okay, so now we ask, what exactly does that mean? Okay, because now that we know what E is bound to an element in the domain. Now we ask, what exactly is this whole thing? Okay, starting from here, ending with this one over here. What is that really saying, in this case? So now I'm going to erase this line here. So now we see this thing ends with a comparison to 1. Okay, it's basically just saying something needs to equal to 1. Alright, so that's a pretty easy concept to understand, right? It's just a regular comparison to a particular integer. Okay, does it equal to 1 or not? Okay, we got that. Okay, so now we look at this portion here, and we are basically looking at things from the outside in, in this particular way. So this entire thing begins with a vertical bar and it ends with a vertical bar. That is the notation of cardinality. Okay, it is asking how many things, how many elements are inside a particular set. That is what it's asking. Okay, so we know it's about cardinality, and this portion here is the set where the cardinality operator is applied on. In other words, we are just trying to count how many things are in this particular set, starting with the starting with the brace, start brace over here and end brace over here. Alright, so we know we are dealing with a set. What about the membership of this set? What qualifies as a member in this set? So now we look into this portion. Okay, this is the portion that defines what is inside the set. And I think I have one extra close parenthesis. Oh, okay, I forgot an open down here. There we go. So now I'm gonna just repeat that one outside now. Okay, EQ such that EQ is an element of F. Okay, so what does that mean? Well, the first thing is this part means that every single element needs to be a 2-tuple in the set that we're considering. Okay, because it's a 2-tuple. The first item binds to the name of E, the second item binds to the name of Q. But hold on a second here, Tech, didn't you already bind E to an element of X? Ah, you're correct, I did. Okay, so that means we don't really have a choice of what this E can be. E has to be a member in the domain already. Okay, that one is kind of stuck already. So we look at Q and go like, looks like we got some flexibility here, right? Because Q can be anything. Wait, hold on a second here, because we got this such that, and the such that is giving you an extra constraint of what can qualify to be an element in this particular set. So what are we using as a constraint? It is this portion. EQ as a 2-tuple, in order to be a member of this set, EQ has to be an element of F. That's the only requirement. Okay. All right. So all that means is, for every single element in the domain, okay, for every single element in the domain, find all the two tuples inside F that start with a specific element in X and make a set out of it. And then we count the number of elements of that set. That count, okay, the cardinality of this set that we are constructing on the fly has to be just one. There can only be one and only one element in that particular set. All right. So how does this apply to all the weird examples that we have talked about in the previous page? Let's take a look. Okay, so we are still staying on the tablet at this point because I want to show you those weird examples that we have used and why each one is going to fail this particular test. So I can do this with a tablet. It's really kind of cool because I can select a portion. Oh, okay, that's way too much. So let's do it one more time. Okay, so let me see if I can. Nope, doesn't let me do it. Okay, now I can specify what I want. Okay, there we go. And then we say copy. And then we paste it here. There we go. And all right. No, we don't want that. Cancel. And it cancels a little bit more than what I expected. There we go. Alright, so I'm just going to erase this portion, that portion. There we go. So it didn't really copy everything because, I need to switch the tool again. Obviously, I have not been doing this enough times to really know the keys. There we go. Alright. So now we have X, which is our domain, Y being our codomain, and we're evaluating F as a set to see whether it is a function or not. Okay? So the first thing is, okay, so according to this statement here, we are evaluating a kind of weird long expression here, but we have to evaluate that expression for every single element of X. And there are two of them, right? So we say, okay, what happens when E equals to the one element, 1 in this case? Alright, so now we try to construct the set on this side. So we're trying to find all the two tuples in F that starts with 1. Okay, we only got 1 here. So we only got one element in the set that we want to construct. And then we take the cardinality of that, and then we compare that to 1. And we say, aha, that is true. Okay, it does equal to 1. So we are good with this particular element. So now we say, but since we need this to be true for every element in the domain, so we want to see if it works with the element 2, because 2 is also in X. So now we construct the set on the fly. The set on the fly that we want to construct says, we are looking for everything, we're looking for all the two tuples in F so that the first element of the two tuple is 2 in this case. In other words, we're looking for all the two tuples that looks like 2 something. And then the answer is none of them. Okay, because when you look at how F is defined here, there's nothing, there are no two tuples, that starts with a 2. So that means the set we're constructing is going to be an empty set. Then we take the cardinality of that, and then we compare that to 1, and the answer is no, it does not equal to 1. So now we got one element that passes this particular test, and then we got another element that fails this test. But because this is a universal quantifier, it is asking everything should pass this test if we want F to be a function. And since we just found one of them not to pass the test, so that means F is not a function. Okay, so I'll just put a big rectangle here and say F is not a function. Okay. What about the other case? Okay, let's go back and pick the other one. which is this one here, which is also not supposed to be a function. Alright, so let's see if I can do this a little bit better this time. Okay, so we'll go ahead and pick everything in here. We copy. And then we paste here. There we go. Alright. Oh, it didn't paste exactly the way I wanted. No. Alright, so let's do that one more time. Tab marker to paste. Alright, so let's paste over here. That looks better. And then we move it around and then erase the other one. Or change the tool. Back to my pen. And then erase the one that was improperly placed. There we go. Alright, so now we ask, what about this f here? Okay, if I want to use x as my domain and I want to use y as my codomain, is this f, okay, this particular definition of f, is it a function? Okay, so we evaluate again. And since the domain has not changed, we have to say, okay, well, let's evaluate for the element 1 in the domain. So we look at this and go like, let's find all the 2 tuples that start with a 1 in F. We got 2 of them, right? We got 1A and we got 1B. So the set that we are constructing on the fly has 2 elements now, 1A and 1B. And then we take the cardinality of that, which means we're just counting the number of items in it. It equals to 1? No, it should equal to 2. So the cardinality equaling to 1 as a comparison is going to fail. This is false. Now, since having one element to fail the test is enough to basically say f is not a function, I can stop here. Okay, there's no need to say, what about 2? No, there's no need to evaluate 2 because if the test fails on at least one element in the domain, it is not a function. Okay, but as an exercise, we want to try that. Okay, so we'll say, what about the case when e equals to 2? So once again, we're constructing a set on the fly that has all the elements that are 2 tuples. The first value in the 2 tuple has to start with a 2 because that's how we bound the value of e, but the second one can be anything. So now we say, we got one of those, right? Because we have 2b in f that meets the requirement that the first item starts with a 2. So now we take the cardinality of that. It does equal to 1. Okay, that's fine. But since we already have one that failed this particular statement, so that means overall f is not a function. Alright, so are we doing okay so far of how we evaluate the expression that is also in the notes and why it is important when it comes to defining whether, in order to define what a function is, the constraint of being a function. So I'm gonna let you guys digest this a little bit and see if there are questions. All right, we got people typing. That's good. All right. So in order for f to be a function, this statement has to be true. But this statement is already having a universal quantifier to begin with. So what that means is for every element in the domain, this condition has to be true. Okay, the constraint has to be met for every single element. And that has to do with the application of the universal quantifier. Alright, so for this, technically Li Yu is wrong. Okay, because 1A, 2B without the curly braces is not a set. But I understand what the question is really asking. I understand what Li Yu is really trying to, what the point that Li Yu is trying to make. But technically, without the curly braces, uh, that f is not a function. Okay, so if you're not looking at the text channel, I'll just go ahead and replicate it here. So when we look at 1a, 2b, this is not a function because it is not even a set. Now, when we look at this, now we can say, aha, now we can see if f is a function. But in order to evaluate whether f is a function or not, my pen doesn't seem to be working. Let me try that one more time. Nope, it just won't work once it gets past it. That is interesting. That part is working, and that part is not working. Huh. Okay, so there's a bug somewhere. Alright, so I'll try to fix the problem. It doesn't. Huh. Alright. So I think I just found a bug on the tablet. Alright, so let's scratch this and we'll write it down here. So f is a set of 1a, 2b, x is 1, 2, y is ab. F is a function that maps x to y is true. Okay. Yes, I just ran out of e-ink. Yolanda, that's funny. Good one. Good one. All right. So this is the case because, the condition that we were talking about, which is this one here, this condition is true for both elements of 1 and 2 in this case. So let me ask you a different question then. What about this one? Okay, what if f is 1a and 2a? Would this f also qualify as a function that maps x to y? X, having x and y being defined exactly the same way as before. So now the question is, what about this particular set f? Okay, is that still considered a function mapping from the domain x to the domain y? The answer is yes. Very good. Yes. So because the quantifier is applied only to elements of x. That is why it still meets that requirement. Okay, because in this case we have to evaluate when e equals to 1. When e equals to 1, the set that we're constructing would have the element of 1a in it. The cardinality of that equaling to 1 is true. When e equals to 2, guess what? We are constructing a set on the fly with 2a in it. The number of elements in that set is also a 1. So when we compare that to 1, it is also returning a true, and that exhausts everything in the domain already. And because for every element in the domain, the constraint is met, and that's why f can be considered as a function mapping from the domain x to the codomain of y. But if somebody's saying, but they're both mapping to the same thing in the codomain, well, the quickest and the most, I guess, pointy answer to that one is, so what? Why is that a problem? The constraint doesn't say that you cannot map multiple things from the domain to the same thing in the codomain. And then somebody else is going to say, but that means the other element in the codomain in B is not mapped to. And same pointy answer. So what? The constraint doesn't say that that cannot happen. Okay? The constraint only says for everything in the domain, everything in the domain must map to one and only one thing in the codomain. It doesn't say anything about uniqueness. Okay, it doesn't say anything about using up everything in the codomain. It said nothing about those two constraints. All right. So I want to make sure that we don't have any further questions about what qualifies a set of two tuples to be a function. Alright, so I'm getting a warning here that says YouTube is not receiving enough video to maintain smooth streaming. I've never gotten this message before. It says error. Okay, but it's just on and off, at two spots of time. One is 109, the other one is 113. It complains that it's, I guess, I'm not streaming, fast enough to YouTube, at certain times. It has never happened to me before, so I'm guessing someone in my household is also streaming something else, using up some of the bandwidth. But the live stream from Discord should still be okay. Alright, so any questions? Okay, got Ivan typing. And when Ivan is typing, I can actually look at the router and see whether it is overwhelmed or not. Just give me a second here. Alrighty. Yeah, I can see potentially there's a problem because my ring camera is also active, because there's motion. So that also uses up some bandwidth. But right now everything is good. Okay. I'm uploading at 3.5 megabits per second, and that's combining the screen share from Discord and also the live stream to YouTube. So together they're using between 3.5 to just jumped all the way up to 4.4. That's just from my computer. And there's nothing else that is streaming anything upstream, so I think that's just temporary. Okay, I think the issue with YouTube should not be persistent. Anyway, so getting back on topic here. So are we okay with section 3.1? How we qualify whether a set of two tuples is a function or not. I want to comment on Ivan's, statement. There's a gamer in the house. Okay, is it true or is it false that there's a gamer in the house? This is classic of what I just mentioned. How natural language is ambiguous because. Okay, so Jonathan is confused about something, but I'm not sure what Jonathan is confused about. But I want to go back to point out the ambiguous part of what Ivan said. Okay, is there is a gamer in the house, or is there a gamer in the house? So I can read that in several ways. Okay, because is there a gamer in the house? Are you asking, is there exactly one gamer in the house? Are you asking, is there at least one gamer in the house? Or are you asking, is there at the most one gamer in the house? Those are the three possible interpretations of the question of, is there a gamer in the house? Okay, or you can also interpret that as, there exists at least one gamer in the house using the existential quantifier. No, we do not need a function. We just need to use precise language. Okay, so we can say, okay, let me switch on the tablet here. Okay, so we can say, okay, existential quantifier x, right? So we say, x is an element of tax household, which is a set of people. Okay. Implies Let's see, do I want to use imply? No, I do not want to use imply in this case. Let's see. No, implies is fine. Implies X is a gamer. Okay. I think this is what Ivan meant, okay? Does at least one X exist such that X is a member of tax household implies X is a gamer. Okay? So why do we need this implication? Why do we need this membership? Because if I don't specify that membership and also the implication, X can bind to you, can bind to someone in your household, right? So if the question is constrained to my household, then I need to use a condition to basically say, okay, if X is not a member of my household, this part of the condition is automatically false, which means the condition is automatically true. Okay. Now, what if that X is bound to someone who is actually in my household? Then we need to evaluate whether X is a gamer or not. So if X is bound to my wife, then the answer is no. Okay, my wife is not a gamer. So that means we have a true implies false, which means the implication is false. Then you guys would say, that makes the quantified statement false. No, that is not the case, because the quantifier is existential. Okay, just having one element, returning a false doesn't make the statement that is quantified by the existential quantifier false. Okay, so we have to evaluate all of the other members. So if X is bound to me, okay, then X is a gamer is true. Okay. I have to think about how to answer that question, because yes, I am a gamer, just not very good at it. Okay, but nonetheless, I spend time in video games. So because I am a gamer and I'm a part of this household, so now we have true implies true, which means the implication is also true. And because we have found at least one person that meets that requirement, that means the entire quantified statement is true. And I think in this case, the use of the implication is incorrect. It needs to be a conjunction. Someone in this household and someone being a gamer. Because otherwise, if X is bound to you and someone in your household, then the existential quantifier is going to be automatically true, and that is not what we want. To answer Jonathan's question, I do play League of Legends, but I only play bot games. That's why I said I'm not a very good one, because I can't stand the heat of playing PvP games. All right, so we are out of time. Okay, so we are out of time. I want you guys to read ahead of me so that on Thursday we can continue on this module, and then we'll talk about why the concept is useful. And also, okay, it won't take you much time to finish this portion, so I also want you to read ahead of me and get to injection, surjection, and bijection. And I'm going to take roll. Okay, I forgot about that. So I'm going to take roll now using a quiz. This is roll taking on today, which is 20210203. And we'll put it in row taking as a category, which basically means the points that you get for row taking does not it's not a part of your actual score. I'm not using row taking to determine letter grade at the end of this class. Alright, so we'll make it due. I'll make it due in what until 2, so that should give you guys plenty of time. So February 3rd, 2 p.m. Okay. Alright, so is that correct? Yep. Okay, so we need to add the question. You guys cannot see it yet because I haven't really released it. So get a new question. I want it to be fill in the blanks, okay? And we'll do the usual thing. Yeah, what is tax word for row taking? And then the answer is Senna. S-E-N-N-A, uppercase S, or S-E-N-N-A with lowercase s. Update question, because last time I forgot to do this and it didn't work. And then we turn that in, and you should be able to see it now. Yes, it is a league reference. That is correct. Yes. Or that, yes, but I don't have the money for that. Alright, so just go ahead and finish the row taking activity, and we are done today. But I also want to remind you guys to read ahead of me, not just the module that we are currently in, but also the next one. So the next one is down here. It talks about injection, surjection, and bijection. It's not there. There's really not a whole lot of new concept or new notations in injection, surjection, and bijection. So it's a really good way to test whether you can apply what we have learned up to this point or not. Okay, so it's kind of a good test to see if you can read and understand that particular module. Yes, so Liu is correct. Okay, it is Senna, S-E-N-N-A. All right. So I'm gonna terminate the voice channel and also the screen sharing, but I will keep an eye on the text channel for maybe another 10 minutes or so, just in case people have any questions about today's lecture. So there we go. Have a good day, and I will see you guys on